Human history is a story told in the language of broken barriers. For millennia, we stood at the edge of vast, churning oceans, seeing them not as a home, but as an impassable void, a line drawn by nature that said, "You shall go no further." And yet, we engineered wood and wind into tools of exploration, and we crossed. We stood at the base of colossal mountain ranges, their jagged peaks scraping the heavens, a vertical wall of stone and ice. And we engineered paths, tools, and techniques, and we climbed. We looked to the sky, a boundless blue dome that held us captive under the laws of gravity. And we engineered wings of metal and harnessed the power of fire, and we flew. We even discovered an invisible wall in the air itself, the sound barrier, a point where the very physics of pressure and flow seemed to forbid further speed. And we engineered a new kind of geometry, a new understanding of aerodynamics, and with a thunderous boom that echoed across the desert, we broke through. Every chapter of our civilization is defined by staring at a line that was declared an absolute limit, and then finding the engineering ingenuity to redraw it. Now, we stand at the shore of the final, ultimate ocean, the cosmic sea, and it presents us with a barrier so fundamental, so deeply woven into the fabric of reality, that it makes mountains look like anthills and oceans like puddles. This is the universe's ultimate speed limit, the speed of light. And this is the story of how we, as engineers, might just be able to break it. This is an engineer's guide to breaking the universe's ultimate speed limit. But to break a rule, you must first understand why it is considered unbreakable. The speed of light in a vacuum, denoted by the simple letter c, is approximately 299,792,458 meters per second. It's a number so large, it's difficult to contextualize. In the time it takes you to blink, a beam of light could circle the Earth more than 7 times. It feels less like a speed and more like an act of instantaneous teleportation. But its true significance isn't its magnitude, it's its meaning. In our everyday experience, speed is a relative concept, a technological challenge. A person can outrun a tortoise, a car can outpace a person, and a jet can outfly a car. Each is just a matter of a more powerful engine, a more efficient design. We are conditioned to see speed limits as suggestions, as records to be broken. But C is different. The speed of light is not a technological benchmark. It is a fundamental law of physics, a cornerstone of Einstein's theory of special relativity. It is less like the world's land speed record and more like the law of gravity. It is not the universe's fastest speed. It is the universe's only true speed. Everything in the cosmos that is without mass travels at this speed, and anything with mass can only ever approach it, but never, ever reach it. So what? Why is this single number the most profound obstacle to our cosmic ambitions? The answer lies in the crushing, soul-breaking tyranny of distance. Our own solar system is vast, but manageable. A journey to Mars takes months. A probe to Pluto takes about a decade. These are human-scale timelines. But the moment we look beyond our stellar nursery, this cosmic speed limit transforms from a high-speed highway into a cosmic prison. Let's take our nearest stellar neighbor, the Proxima Centauri system, just over 4 light-years away. A light-year is the distance light travels in a year, a measure of distance. Not time, that is already staggering. About 9.5 trillion kilometers. Traveling at the speed of light, a theoretical maximum we can't even reach, it would take a crew over 4 years to arrive. But for a real spacecraft, one with mass, the problem becomes exponentially worse. According to relativity, as an object with mass accelerates closer and closer to the speed of light, its relativistic mass increases. It effectively becomes heavier and heavier, requiring more and more energy for each tiny increase in speed. The energy required to accelerate a single starship to, say, 99.9%, the speed of light would exceed the total energy consumption of our entire global civilization for centuries. The physics acts like an infinite headwind, pushing back harder the faster you go. Until you are demanding infinite energy to reach a finite speed. It's the universe's way of saying no. And what does this mean for our dreams of a galactic civilization? The Milky Way galaxy, our home, is about 100,000 light years across. To cross it, even in a hypothetical ship traveling at an impossible 99.99% of c, would take over 100,000 years from the perspective of an observer on Earth. The crew might experience a shorter journey due to time dilation, but upon their arrival, everyone they ever knew, every nation they were a part of, the very languages they spoke, would have vanished into the mists of deep time. The Andromeda Galaxy, our closest major galactic neighbor, is 2.5 million light-years away. That journey isn't a historical event. It's a geological one. This isn't a challenge of engineering a better engine. This is a fundamental mismatch between the scale of our lives and the scale of our universe. C is the law that sentences a species born on one tiny planet to eternal confinement in its own cosmic backyard. But our investigation today is about a far more audacious goal. We're not just aiming to cross the galaxy. Our title makes a bolder promise: to travel to the other side of the universe. This is where the problem metastasizes from merely impossible to conceptually nonsensical. The observable universe, the sphere of cosmos, from which light has had time to reach us since the Big Bang, is estimated to be about 93 billion light-years in diameter. The number is so vast that it's functionally meaningless without an analogy. Imagine our entire Milky Way galaxy with its hundreds of billions of stars. Its nebulae, its black holes, was shrunk down to the size of a single grain of sand. At that scale, the observable universe would be a sphere of sand more than 1.5 kilometers, or nearly a mile, across. A journey from one grain of sand to another on the opposite side of this sphere, traveling at the universe's absolute, unbreakable speed limit, would take 93 billion years. Let that number sink in. The universe itself is only about 13.8 billion years old. Your journey would require more than 6 times the entire history of time, space, and existence. You would be a tourist arriving at a destination that had long since cooled, faded, and died before you were even halfway there. This is the first and most obvious reason why our engineering challenge seems like a closed case. The distances are not just vast, they are transcendentally, cosmically absurd. The speed limit is too slow. The universe is too big. End of story. Case closed. Except the situation is even worse. The universe has another, even more insidious rule that makes this journey impossible. The distances we've been discussing are not static. The very fabric of spacetime is expanding. It's a discovery made by Edwin Hubble that completely rewrote our understanding of the cosmos. He observed that distant galaxies are all moving away from us, and the farther away they are, the faster they are receding. This is not because the galaxies are flying through space like cosmic shrapnel from the Big Bang. Instead, the space between us and those galaxies is actively stretching, carrying them along for the ride. To understand this, imagine you are on an unpowered raft in the middle of the ocean, and your destination is a distant island. Now, imagine that the ocean itself is not a fixed body of water, but a magical, expanding substance. The water right around you is stretching slowly, but the water farther away is stretching much faster. The island you want to reach isn't just far away. The very sea between you and it is growing wider every single second. This is our cosmic predicament. And it gets worse. This expansion is accelerating, driven by a mysterious force we've labeled dark energy. After a certain distance from us, a point known as the Hubble horizon, the rate of expansion of space becomes so great that it exceeds the speed of light. This does not violate Einstein's theory, because nothing is moving through space faster than light. It is space itself that is expanding and carrying the galaxies away at superluminal speeds. Let's return to our engineering problem. What does this mean for our journey to the other side of the universe? It means that our destination is receding from us faster than we could ever hope to travel. It's like trying to run up a downward moving escalator, but this escalator's steps are moving away from you faster than your legs can possibly carry you. You can run at your maximum possible speed, the speed of light forever, and you will not only fail to reach the top, but you will find yourself carried further and further down. This isn't a wall we can hope to punch through with more thrust or a more efficient engine. This is a geometric checkmate. The very arena of our travel is working against us in the most fundamental way imaginable. It is a cosmic no trespassing sign written into the laws of geometry and expansion. So, the case file seems to be overflowing with evidence for impossibility. We have Exhibit A, the unbreakable light speed barrier, which turns interstellar travel into a multi-generational crawl. We have Exhibit B, the sheer scale of the universe, which makes travel times longer than the age of existence itself. And we have Exhibit C, the accelerating expansion of space-time, which places our ultimate destination on a cosmic treadmill, pulling it away from us faster than we can ever run. Any sane, conventional engineer looking at this evidence would stamp the file impossible, close the case, and move on to more practical problems. But we are not conventional engineers. We are cosmic engineering detectives. And when the direct path is blocked by insurmountable walls, a detective doesn't give up. A detective looks for a secret passage, a loophole, a hidden clue that changes the entire nature of the problem. And this is where our investigation truly begins. We have been asking the wrong question. All of our assumptions of impossibility are based on one flawed premise, that we must travel through space. We have been acting like a car driver, trying to get from one side of a mountain to the other, seeing only the long, winding road that goes around it. The true engineering solution is not to build a faster car, but to question the mountain itself. What if we could build a tunnel? What if we could bend the very landscape to our will? This is the pivot. We must stop thinking of space-time as a static, immutable stage on which events unfold. We must start seeing it for what general relativity tells us it is: a dynamic, pliable, geometric fabric that can be bent, warped, stretched, and perhaps even torn. The laws of physics are not just a list of restrictions. They are an instruction manual. And deep within the complex equations of Einstein's theories are whispers of profound possibilities. The possibility that two distant points in space-time can be connected. The possibility that we could warp the space around a ship to move the destination toward us, rather than moving the ship toward the destination. The framework for breaking the universe's ultimate speed limit has been hiding in plain sight for over a century. The path forward is not through brute force propulsion, but through elegant, audacious, cosmic-scale civil engineering. We are not aiming to build a faster ship. We are aiming to build a better road. This, then, is the foundation of our guide. The journey to the other side of the universe is not impossible because our technology is too primitive. It is impossible only if we limit our thinking to a primitive approach. The clues are all there, hidden in the mathematics of general relativity and theoretical physics. They speak of concepts that sound like science fiction. Einstein-Rosen bridges, more commonly known as wormholes. Alcubierre drives, or warp bubbles, that compress space in front of them and expand it behind. These are not fantasies born from a writer's imagination. They are plausible, albeit monumentally difficult, engineering solutions that arise from our deepest understanding of how the universe works. Our investigation will not be about designing a bigger rocket engine. It will be about understanding the fundamental properties of space-time itself as a raw, engineerable material. We will explore the physics that could allow for these cosmic shortcuts and the almost unimaginable technological hurdles we would need to overcome to build them. We will move beyond the question of, can we go faster? And into the realm of, can we redefine distance itself? The ultimate speed limit is only a limit if you play by the conventional rules. Our mission as cosmic engineers is to learn how to rewrite them. We will not be passengers traveling within the universe. We will seek to become architects of its very geometry. The case is not closed. It is just beginning. In our introduction, we established the colossal scale of our challenge. We identified the walls standing between humanity and the stars, the speed of light, and the universe's relentless expansion. Now, in this phase of our investigation, we move from the what to the why. We must become forensic physicists, meticulously examining the laws that construct these barriers. This is not a matter of opinion or technological pessimism. It is a case built on the hardest evidence the cosmos can provide. To understand how we might one day break the rules, we must first appreciate, in excruciating detail, why they are considered the most perfect, unbreakable laws in all of nature. Our prime suspect, the origin point for all of this impossibility, is not a complex 10-page equation, but two deceptively simple postulates that form the foundation of Albert Einstein's special theory of relativity. The first postulate is almost common sense. The laws of physics are the same for everyone, as long as you are not accelerating. It means that an experiment conducted on a smoothly moving train will yield the exact same results as one conducted standing on the ground. This is the principle of relativity, a concept that dates back to Galileo. It's the second postulate, however, that throws a wrench into the machinery of our intuition. It states that the speed of light in a vacuum, c, is the same for all observers, no matter how fast they are moving or how fast the source of the light is moving. This sounds simple, but it is profoundly bizarre and contradicts every ounce of our daily experience. Imagine you're on a high-speed train moving at 500 kilometers per hour. You throw a baseball forward down the aisle at 100 kilometers per hour. For you, on the train, the ball's speed is 100. But for an observer standing on the platform watching you pass, the speed of the ball is the train speed plus the ball's speed, 600 kilometers per hour. Speeds add up. It's simple, it's intuitive, and it's how the world works. But if you were to stand on that same train and turn on a flashlight, something magical happens. You would measure the speed of a light beam moving away from you at sea. The observer on the platform, watching the light from your moving flashlight, would also measure its speed as c, not c plus 500 kilometers per hour, just c. This has been confirmed by countless experiments. The universe is somehow configured to ensure that this one specific speed is an absolute constant for everyone. And from this one strange, unyielding fact, all the paradoxes and impossibilities of high-speed travel are born. The universe bends time, it warps distance, and it rewrites the rules of energy and mass, all in service of keeping the speed of light constant. The first consequences of this cosmic conspiracy to protect c are the famous concepts of time dilation and length contraction. As a spaceship accelerates to a significant fraction of the speed of light, an observer on Earth would see two strange things happen. The ship's clock would appear to tick slower than their own, and the ship itself would appear to be physically compressed in its direction of travel. These are not optical illusions. For the universe, time and space are not rigid, absolute backdrops. They are flexible, interwoven components on a single fabric, space-time. To keep c constant, space-time itself will stretch and squeeze. For the crew on board, time would feel perfectly normal. But upon returning from a journey to a nearby star that took them, say, 10 years of their own subjective time, they could find that 50 years have passed on Earth. This effect is a double-edged sword. While it offers a form of biological time travel into the future and makes long journeys subjectively bearable for the crew, it shatters any hope of a cohesive interstellar society. You cannot have a conversation with a colony world if the round-trip message takes a century. You cannot build an empire if your fleets return to a home that has forgotten they even existed. But this is merely a sociological problem. The true engineering challenge, the one that grinds our ambitions to dust, is found in the physics of mass and energy. This is the heart of our impossible challenge, the concept of relativistic mass. In classical Newtonian physics, mass is a constant. An object has a certain amount of stuff in it, and that's that. To make it go faster, you apply a force, and its speed increases in a predictable, linear way. But Einstein revealed a far deeper truth with the most famous equation in history. E equals mc. Energy and mass are not separate entities. They are two sides of the same coin. They are convertible. And this is precisely what happens when you try to accelerate an object with mass. As you pump kinetic energy into your starship, the universe doesn't just translate that energy into pure velocity. As your speed climbs closer and closer to c, a larger and larger fraction of the energy you add is converted directly into mass. To visualize this, imagine you are pushing a simple shopping cart across an infinitely long floor. At first, it's easy, but as you push it faster, invisible hands start adding bricks to the cart. At slow, everyday speeds, you don't notice a thing. But as you approach a significant fraction of c, the hands start adding bricks at a frantic pace. By the time your cart reaches 86.6% the speed of light, its mass has doubled. It's twice as hard to push. At 99.5% the speed of light, its mass has increased by a factor of 10. To gain that last tiny fraction of speed, you are now pushing a cart that weighs as much as a truck. At 99.999% the speed of light, its mass has increased by a factor of over 223. It now weighs as much as a freight train. The speed of light is an asymptote, a finish line that you can run towards forever. But the closer you get, the heavier your own body becomes, until at the very threshold of c, you would have to move an object of infinite mass. The universe forbids you from reaching its ultimate speed by making you infinitely heavy. This isn't a technological problem. This isn't a matter of building a better engine. This is a fundamental property of matter, energy, time, and space. So, what does this mean in terms of an engineering budget? Let's put some numbers to it. Let's design a hypothetical, yet modest, interstellar starship. We'll call it the Starchaser. It has no fuel, no engines, no crew, just the dry mass of the vessel itself. We'll make it 100,000 metric tons, roughly the mass of a Nimitz-class aircraft carrier. A significant, but not unimaginable, piece of engineering. Now, let's calculate the kinetic energy required to get the Starchaser up to relativistic speeds. The currency of the universe is energy, and the price of speed is exorbitant. To accelerate the Starchaser to just 50% of the speed of light, the kinetic energy required would be approximately 1.4 x 1023 joules. This number is so large, it's meaningless. So let's convert it. The entire annual energy consumption of human civilization on Earth is about 6 by 1020 joules. That means to get our single, empty ship to just half the speed of light would require more than 230 times the energy our entire species uses in a year for everything heating, industry, transportation, everything. But 50% of c is not nearly fast enough for interstellar travel. Let's get more ambitious. Let's push the Starchaser to 99% of the speed of light. Because of the brutal mathematics of relativistic mass increase, the energy cost skyrockets. The kinetic energy required is now a staggering 8.2x y a joules. That's more than 13,600 times the world's annual energy usage. It's an amount of energy equivalent to what the sun, a gargantuan thermonuclear furnace, radiates in about 21 seconds. We are no longer talking about the energy budget of a planet. We are talking about the energy budget of a star. But what about 99.99% of c? The energy required balloons to 9.6 x 1025 joules. To accelerate one aircraft carrier to this speed, we would need to capture and store the full, untamed power of our sun for nearly 5 minutes straight. The engineering challenge is no longer about building a ship. It is about building a machine that can harness the power of a god. And even if we could somehow generate and store this stellar-scale energy, we face a final logistical checkmate, the tyranny of the rocket equation. Formulated by Konstantin Tsiolkovsky, the rocket equation governs how much fuel a rocket needs. In essence, it says that to accelerate, you must throw mass out the back. But the fuel you need to do this also has mass, and you need to burn more fuel just to accelerate the fuel you haven't burned yet. It's a vicious cycle of diminishing returns. For our star chaser, let's assume we have the most perfect, most efficient fuel theoretically possible: matter-antimatter annihilation. When a particle of matter meets its antimatter counterpart, they annihilate each other, converting 100% of their mass into pure energy. A perfect realization of EE, Kyle's MC. It is the ultimate fuel. So, how much of this perfect fuel do we need to get our 100,000-ton ship to 99% of the speed of light? The answer is heartbreakingly absurd. You would need approximately 1.4 million tons of matter-antimatter fuel. That means our final rocket would consist of a 100,000-ton payload attached to a fuel tank 14 times more massive than itself. The ship is no longer a ship. It is a tiny capsule strapped to the front of a colossal, universe-ending bomb. Because the accidental detonation of that much antimatter would release more energy than the asteroid that wiped out the dinosaurs. And this is the best-case scenario, with perfect engines and perfect fuel. Any other propulsion method, from fusion rockets to solar sails, is orders of magnitude less efficient and requires fuel loads that are not just massive, but physically nonsensical, requiring more fuel than there are atoms in the galaxy. The direct approach to breaking the speed of light is not just a hard engineering problem. It is a dead end, sealed by the laws of physics on one side and the laws of logistics on the other. The case file is closed. In the first phase of our investigation, we built an airtight case for the prosecution. We demonstrated how the laws of special relativity, the relentless increase of relativistic mass, and the impossible calculus of energy form a prison of perfect, inescapable walls. We proved, using the universe's own rulebook, that any direct brute force attempt to travel across the cosmos at meaningful speeds is doomed to fail. The case file is stamped impossible. And if our investigation ended there, we would be left with a profound sense of cosmic loneliness, a species with interstellar dreams trapped in a planetary cradle. But our work as cosmic engineering detectives has only just begun. When the front door is barred and locked with the chains of unyielding physics, a detective does not walk away. They begin to examine the architecture of the building itself, looking for hidden passages, structural weaknesses, and secret keys. The key to our case, the clue that reopens the entire investigation, lies in moving beyond Einstein's first masterpiece, special relativity, and into the mind-bending landscape of his second, the general theory of relativity. Special relativity, for all its power, is fundamentally a theory of flat, empty space. It provides the rigid, unbending rules for cause and effect on a perfectly level playing field. It's the law of the cosmic highway. General relativity, however, is a theory about the highway itself. It reveals that the playing field is not level. The stage is not static. The fabric of space-time is not a rigid backdrop, but a dynamic, active participant in the cosmic drama. The central idea of general relativity is one of the most profound and elegant shifts in the history of science. Gravity is not a force. For centuries, we pictured gravity as an invisible rope, a mysterious action at a distance, where massive objects like the sun reached out across the void to pull on planets like the Earth. Einstein offered a revolutionary new perspective. He proposed that mass and energy do not create a force. Instead, they fundamentally alter the geometry of the universe around them. They curve the very fabric of space-time. The classic analogy is a heavy bowling ball placed on a stretched rubber sheet. The ball creates a deep depression, a curve in the sheet surface. A smaller marble rolled nearby doesn't get pulled towards the bowling ball by some mysterious force. Instead, it simply follows the straightest possible path across the now curved surface, which guides it into an orbit around the central mass. The Earth is not being pulled by the sun. The Earth is moving in a straight line through space-time that has been warped by the sun's mass. This is our first and most important clue. Why? Because if space-time can be bent, it means it is a physical, manipulable medium. It is not an abstract concept. It is an engineering material. And if the universe can shape it, then the ultimate engineering challenge is to figure out if we can shape it too. This isn't just a beautiful theory. The cosmos provides us with direct, observable evidence that this warping of reality is happening all around us. This is our cosmic clue number 1, gravitational lensing. Because space-time is curved by mass, the path of anything traveling through it, including light, must also be curved. In 1919, a solar eclipse expedition led by Sir Arthur Eddington provided the first proof. By observing starlight passing near the sun's limb, they saw that the stars' positions appeared to shift, their light bent by the sun's gravity, exactly as Einstein's equations predicted. Today, with powerful telescopes like Hubble and the James Webb, we see this phenomenon on a galactic scale. When we look at a distant quasar that lies behind a massive galaxy cluster, the cluster's immense gravity acts like a cosmic lens. It warps the space-time around it so severely that the light from the quasar is bent and magnified, sometimes creating multiple distinct images of the very same object, or smearing its light into spectacular arcs and rings known as Einstein rings. So what does this mean for our investigation? It is cosmic-scale, irrefutable proof that the geometry of the universe can be altered to change the path of light. It demonstrates that the shortest distance between 2 points in spacetime is not always a straight line in the way we perceive it. The universe itself, using the tool of gravity, creates cosmic detours and shortcuts. This observation transforms our entire engineering perspective. We have been obsessed with the speed of our vehicle. Gravitational lensing proves that it might be more important to focus on the shape of the road. The universe is showing us, on the grandest possible scale, that the fabric of reality is pliable. The detective asks, if a galaxy can do this by accident, could a sufficiently advanced civilization do it on purpose? Our second clue comes from a phenomenon we previously identified as a barrier, the expansion of the universe. In our initial analysis, the fact that distant galaxies are receding from us faster than the speed of light seemed like the final nail in the coffin for interstellar travel. It was a geometric checkmate. But a good detective knows that a piece of evidence can look entirely different when viewed from a new angle. Let's re-examine that fact. The space between us and a galaxy on the other side of the observable universe is stretching so fast that the galaxy is being carried away from us at superluminal speeds. The crucial point here is that the galaxy itself is not moving through space at that speed. It is likely moving quite slowly within its own local patch of spacetime. It is the fabric of space itself that is doing the moving. And this is the monumental loophole we have been searching for. Einstein's speed limit, c, is a local law. It means that within any given patch of spacetime, you cannot travel from point A to point B faster than light. It governs the motion of objects within the cosmic sea. But the cosmic sea itself has no speed limit. The fabric of reality can stretch, expand, and as we will see, potentially contract at any speed it likes. The speed limit applies to the ship, not to the ocean. So what? What is the engineering implication of this clue? It fundamentally reframes our goal. We don't need to break the local speed limit. We need to find a way to replicate the universe's own trick. If space-time can be made to expand behind our ship and contract in front of it, our vessel could be carried along in a bubble of spacetime, much like a surfer riding a wave. The ship would remain stationary within its local bubble, never violating the local speed limit, while the bubble itself could traverse the cosmos at potentially limitless speeds. The expansion of the universe, once our ultimate barrier, has just become our most promising clue, proving that superluminal travel is not against the laws of physics. It is a known, observable feature of the universe's own behavior. Our third and final clue takes us to the most extreme and mysterious objects in the entire cosmos: black holes. A black hole is what happens when mass is so concentrated that the curvature of spacetime becomes, for all practical purposes, infinite. The bowling ball on the rubber sheet analogy breaks down here. A black hole is not a dip in the sheet. It is a puncture, a tier that leads to a place where our understanding of physics ceases to function, a singularity. Surrounding this singularity is the event horizon, a boundary that is not a physical surface, but a geometric one. It is the point of no return, the point where the curvature of spacetime is so steep that the escape velocity exceeds the speed of light. Nothing, not even light itself, can escape its grasp once it crosses this threshold. To an engineer, a black hole is the ultimate materials testing laboratory. It shows us the absolute limits of what spacetime can do. It proves that the fabric of reality is not just bendable, but can be twisted, stretched, and distorted into the most extreme configurations imaginable. And at its heart is the singularity, a place where density and gravity are infinite, where time and space are so warped that they may well lose their meaning. So what is the clue here? The existence of black holes and singularities suggests that the topology of spacetime, its fundamental shape and connectedness, might be far more complex than the simple flat sheet we perceive. Physicists have long theorized that these extreme distortions could lead to topological shortcuts. What if the puncture in spacetime caused by one black hole could somehow connect to a different puncture somewhere else in the cosmos? This concept, a tunnel through spacetime, is what we call a wormhole, or an Einstein-Rosen bridge. Black holes, in their violent, reality-shattering existence, provide a tantalizing clue that such tunnels might be a natural, if exotic, feature of cosmic geometry. So let's gather our clues and lay them out on the investigation board. Our shift from special to general relativity has completely changed the case. Clue number 1. Gravitational lensing proves that spacetime's geometry is mutable and that we can alter the path of light. Clue number 2. Cosmic expansion proves that spacetime itself is not bound by the speed of light, providing a fundamental loophole for superluminal travel. And clue number 3, black holes, demonstrates that spacetime can be twisted into extreme topological configurations, hinting at the physical possibility of shortcuts or tunnels. When we synthesize this evidence, a new picture emerges. We are no longer looking at a set of rigid, restrictive laws. We are looking at the foundational principles of an entirely new field of engineering. Let's call it metric engineering. The engineering of the metric tensor, the mathematical object in general relativity that defines the geometry of space and the flow of time at every point in the universe. Our goal is no longer to build a more powerful rocket engine. Our new goal is to master the mathematics and technology required to warp, bend, and fold the metric itself. We must stop thinking like travelers trying to cross a vast, empty ocean. We must start thinking like cosmic civil engineers, capable of building bridges, digging tunnels, and surfing the very waves of spacetime. The evidence is clear. The universe is not a static prison. It is a dynamic, pliable landscape. And we have just found the first clues that tell us how we might one day become its architects. Our investigation has reached a critical turning point. In phase 1, we stood before the monolith of impossibility, the laws of special relativity, which proved with cold, hard mathematics that our ambitions were futile. In phase 2, we became cosmic detectives, dusting for fingerprints on the fabric of reality itself and discovering crucial clues in general relativity. That spacetime is a pliable material, that it can expand faster than light, and that it can be twisted into extreme topological shapes. We have established motive and opportunity. The universe has the means to allow for faster than light travel. Now in phase 3, we transition from detective to inventor. We must connect these abstract clues to concrete engineering blueprints. This is the moment of synthesis, the eureka flash, where observation gives birth to design. We are about to lay out the technical thesis for how humanity could build a machine that breaks the ultimate speed limit, not by violating the laws of physics, but by exploiting them in the most ingenious way imaginable. Our first blueprint is born from cosmic clue number 3, the extreme topology of black holes. These objects prove that spacetime can be punctured and distorted. This leads us directly to the concept of an Einstein-Rosen bridge, better known as a wormhole. A wormhole is a theoretical shortcut, a tunnel through the bulk of spacetime itself. The most effective analogy is to imagine our universe as a vast, flat sheet of paper. To get from one point on the paper to another, an ant would have to crawl the entire distance across the two-dimensional surface. This is conventional, sublight travel. But if we were to take that sheet of paper and fold it over, bringing the ant's starting point directly above its destination, we could then punch a hole through the paper, creating a three-dimensional tunnel. The ant could simply step through this tunnel, traversing a colossal distance in mere moments. That is precisely what a wormhole proposes to do. It connects two distant regions of our three-dimensional space by creating a tunnel through a higher, fourth spatial dimension we often call hyperspace. In engineering terms, this is the ultimate bypass, a cosmic subway system that renders conventional distance obsolete. You wouldn't be traveling through space faster than light. You would be taking a path where the journey itself is fundamentally shorter. But a theoretical blueprint is not a viable machine. The engineering challenges to building a stable, traversable wormhole are monumental, and Einstein's own equations reveal the first critical flaw. General relativity predicts that any wormhole large enough for a person or ship to enter would be catastrophically unstable. Its throat would pinch shut with infinite speed the moment the slightest bit of matter or energy tried to pass through it, likely creating a singularity. It would be a tunnel that slams its doors shut the instant you tried to use it. For decades, this instability made wormholes a mere mathematical curiosity. But this is where the ingenious connection is made. The problem, it turns out, is not with the geometry, but with the material used to build it. All known forms of matter and energy stars, planets, radiation, you possess a positive energy density. This positive energy is what causes space-time to curve in the familiar, attractive way we call gravity. It's what makes the bowling ball create a dip in the rubber sheet. To counteract the wormhole's tendency to collapse, you would need to prop its throat open. You would need to line it with a substance that curves space-time in the exact opposite way. You would need a material that generates a kind of anti-gravity, pushing the walls of the tunnel apart. This brings us to our first technical thesis. The viability of a wormhole depends entirely on the existence of exotic matter, a theoretical substance defined by its property of having a negative energy density. This material would be unlike anything we have ever witnessed. It would possess repulsive gravitational properties. It is the architectural scaffolding required to turn a fleeting mathematical possibility into a stable, traversable piece of cosmic infrastructure. The engineering problem of building a shortcut across. The universe has just been redefined as a materials science problem. Can we create and control exotic matter? Our second blueprint for faster-than-light travel arises from cosmic. Clue number 2, the observation that space-time itself can expand faster than light. If the fabric of reality is not bound by c, can we engineer a solution that leverages this property? The answer is a resounding perhaps, and it comes in the form of the Alcubierre drive, or what is more popularly known as a warp drive. Proposed in 1994, by physicist Miguel Alcubierre, this is not a topological shortcut, but a dynamic propulsion system. It works by warping space around a vessel, rather than propelling the vessel through space. Imagine a surfer on an ocean wave. The surfer isn't swimming through the water at the speed of the wave. They are largely stationary on their board, while the wave itself, a disturbance in the medium of the water, carries them forward. The Alcubierre drive aims to do the same with the medium of spacetime. The engineering design requires generating an intense, localized distortion of spacetime geometry. In front of the ship, spacetime would be engineered to contract, effectively pulling the destination closer. Behind the ship, spacetime would be made to rapidly expand, pushing the starting point further away. The ship itself would rest inside a warp bubble of flat, undisturbed spacetime, completely isolated from the tidal forces outside. Inside this bubble, the crew would feel no acceleration, no crushing g-forces. They would, in essence, be motionless in their local frame of reference, while their bubble of reality is ferried across the cosmos at potentially thousands of times the speed of light. They would be stationary passengers on a wave of pure geometry. This blueprint seems radically different from a wormhole. One is a static tunnel, the other is a dynamic wave. One is a bridge, the other is a ship. Yet as we drill down into the engineering requirements of the Alcubierre drive, our investigation leads us to a stunning revelation. To create the expanding spacetime required behind the ship, Alcubierre's solution to Einstein's field equations makes one absolute, non-negotiable demand. It requires the presence of a region with negative energy density. It requires, once again, the exact same theoretical substance, exotic matter. Without this repulsive anti-gravitational material, the wave cannot be formed. The space-time expansion cannot be generated. The warp bubble cannot exist. This is the eureka moment of our entire investigation. We have just taken two completely independent, theoretically plausible pathways to breaking the light-speed barrier and discovered that they both run through the exact same, impossibly narrow choke point. The grand challenge of interstellar travel, a problem of distance, energy, and speed, has been refined and distilled into a single unifying technical thesis. The key to unlocking the cosmos, whether through a wormhole's tunnel or a warp drive's wave, is the mastery of negative energy. The entire case now rests on one pivotal question. Is exotic matter with negative energy density a mere mathematical fantasy? Or is it allowed by the known laws of physics? For a long time, the answer seemed to be a definitive no. The idea of matter with repulsive gravity felt like a violation of common sense and energy conservation laws. It was the unobtainium of theoretical physics. But then, a subtle clue emerged, not from the depths of cosmic observation, but from the strange and counterintuitive world of quantum mechanics. This clue is called the Casimir effect. In classical physics, a vacuum is the definition of nothingness. It is empty, with zero energy. But quantum field theory revealed that the vacuum is, in fact, a seething, effervescent soup of virtual particles, constantly popping into and out of existence. It is filled with a background level of energy, known as zero-point energy. The Casimir effect, predicted in 1948, and experimentally verified multiple times since, describes what happens when you place two uncharged, perfectly parallel conductive plates extremely close to each other in this vacuum. The tiny space between the plates restricts the wavelengths of the virtual particles that can exist there, while the space outside has no such restriction. This results in there being less quantum energy between the plates than outside of them. The energy density in the gap becomes lower than the surrounding vacuum's zero-point energy. It becomes, in effect, a region of negative energy density. And this energy difference creates a real measurable force, pushing the plates together. The Casimir effect is our proof of concept. It is a laboratory-verified demonstration that regions of negative energy density are not forbidden by the laws of nature. The universe allows them to exist. The effect is, of course, infinitesimally small, and generating enough of it to stabilize a wormhole or power a warp drive is a challenge of a completely different order of magnitude. But it is a crack in the wall of impossibility. It is a whisper from the quantum realm that the exotic matter we need is not a fiction. It is a real physical phenomenon waiting for an engineering team clever enough to figure out how to amplify and control it. The path to the stars is paved with negative energy, and for the first time in our investigation, we have found a clue that suggests the paving stones might actually exist. Our investigation has led us through a labyrinth of cosmic law. We began with the ironclad walls of impossibility erected by special relativity. We then discovered hidden clues in the flexible, dynamic geometry of general relativity. And finally, we synthesized these clues into a single, unifying technical thesis, the mastery of negative energy via the engineering of exotic matter is the key to unlocking faster-than-light travel. The detective work is over. The case is solved, not with a culprit, but with a blueprint. Now, the most challenging phase begins. We must transition from the role of investigator to that of chief engineer. We must formulate a project plan for the single greatest undertaking in the history of our species, a multi-generational effort to transform a glimmer of quantum possibility into a fleet of star-faring vessels. This is the roadmap to the stars, a construction plan that will require a complete reimagining of science, industry, and human ambition. The first phase of this grand project does not begin with building a starship. It does not even begin with building a foundry. It begins in the quietest, coldest, and most meticulously controlled laboratories on Earth. It begins with the first step of any engineering revolution, mastering the foundational science. We call this phase 1, quantum amplification. Our only empirical handle on negative energy is the Casimir effect, a whisper from the quantum vacuum. Today, it is a scientific curiosity, a microscopic force that validates a theoretical principle. The goal of phase 1 is to transform it from a passive effect to be observed into an active force to be controlled. This is the engineering equivalent of humanity's first encounter with fire. Our ancestors saw it flash in the form of lightning, a wild, untamable force of nature. Their first challenge was not to build a furnace, but simply to capture a single spark, to learn how to sustain it, and to keep it from dying out. Our first challenge is the same. We must develop the quantum engineering techniques to not just measure the Casimir effect, but to amplify it. This would likely involve the creation of exotic metamaterials with structures engineered at the atomic scale, designed to manipulate the quantum vacuum in ways we can currently only dream of. It would require a level of control over quantum fields that would make the Large Hadron Collider look like a simple workshop tool. This phase would take decades, perhaps a century, of focused fundamental research. Its sole deliverable would not be a machine, but a seed, a stable, containable, and controllable microgram of negative energy. A single glowing ember of impossibility made real. Once we have captured the spark, we must learn to build the furnace. Phase 2, macroscopic stabilization and production. This is the industrial revolution of our new physics. The goal of this phase is to scale up the production of exotic matter from the microscopic to the macroscopic. This means building an entirely new kind of industrial facility, a place that we might call an exotic matter foundry. The energy requirements for such a facility would be staggering. The laws of physics suggest that to create a region of negative energy, you must expend a colossal amount of positive energy around it. We are not talking about the output of a power plant, or even a nation. We are likely talking about the power output of a planet. The construction of this foundry would necessitate a global scale, perhaps even solar system scale, energy infrastructure, like a Dyson swarm capturing a significant fraction of our sun's output. And then there's the problem of containment. How do you hold a substance whose defining characteristic is that it repels the geometry of space-time? A magnetic bottle, like in a fusion reactor, might not be sufficient. We would need to engineer containment fields of pure geometry, sculpting space-time itself into a cage to hold its antithesis. This phase represents a leap in engineering scale unprecedented in history. It would be a project that would make the construction of the pyramids seem like a weekend hobby. The outcome of phase 2 would be a tangible supply of our miracle ingredient, perhaps kilograms or even tons of it, held in a state of perfect stability, ready for the final stage of manufacturing. With a viable supply of our construction material, we enter the final and most spectacular stage of the project, phase 3, geometric shaping and deployment. This is where we finally build the machines that will take us to the stars. The path here diverges depending on which blueprint we choose to follow. If we pursue the Alcubierre warp drive, this phase is about manufacturing and precision assembly. The exotic matter produced in our foundry would need to be forged into a perfect, hyperdense torus, a donut shape of specific thickness and diameter that would encircle the starship. This is not blacksmithing. This is geometric engineering at the atomic level. The slightest imperfection in the density or shape of the ring could cause the warp bubble to become unstable or collapse entirely. The starship itself would be built within this ring, a vessel designed not with massive engines, but with incredibly sophisticated field generators to control and modulate the negative energy in the torus, allowing the pilot to form, sustain, and navigate the bubble of warp spacetime. The alternative path is the wormhole. Here, the engineering is perhaps even more audacious. We would begin by capturing or creating two entangled microscopic wormholes in our laboratory. Then, we would feed one mouth of the wormhole with our exotic matter, causing it to inflate to a macroscopic, traversable size, perhaps meters or even kilometers in diameter, stabilized by a scaffolding of repulsive gravity. This mouth would be kept in a fixed position, say, in a stable orbit around Saturn. The other mouth, still connected through hyperspace, would be loaded onto a conventional sublight tug ship and physically transported to our destination. For decades, it would crawl through interstellar space at a fraction of the speed of light, heading for Alpha Centauri. Upon its arrival, the wormhole would be anchored in place, and the bridge would be open. The journey that took the tug ship 40 years could now be made in an instant. We would have built our first stable gate, our first permanent archway to another star system. Successfully building such a machine, whether a ship or a gate, would represent the single greatest technical achievement in human history. But its true significance would not be in the technology itself, but in the legacy it creates for all future generations of humanity. This is the so what on a civilizational scale. The first and most immediate impact would be the end of scarcity. For our entire history, we have been a species defined by the finite resources of one small planet. An interstellar humanity would have access to the unimaginable wealth of entire solar systems. We could mine asteroid belts rich in metals that are rare on Earth, harvest isotopes for clean energy from the atmospheres of gas giants, and draw upon the light of multiple suns. The concept of resource wars, of poverty driven by lack, would become an archaic relic of our planetary childhood. The second legacy would be the end of isolation. As a species confined to one planet, we are a single point of failure. A sufficiently large asteroid, a runaway pandemic, or a self-inflicted global catastrophe could end our story permanently. By establishing self-sufficient colonies on worlds orbiting other stars, humanity would guarantee its survival. We would become a resilient, distributed, and truly cosmic species, our consciousness no longer held in one fragile basket. But the most profound legacy would be the dawn of a new renaissance. Imagine the explosion of knowledge. We would transition from a species that studies one biosphere, one geology, one planetary system, to a species that can engage in comparative xenobiology, studying the unique evolutions of life on other worlds. We would practice comparative geology on planets with iron cores and methane seas. We would witness stellar phenomena up close that we can currently only glimpse through the faint light of our telescopes. Every new system visited would unlock a library of new scientific truths, and with this new knowledge would come a new flowering of art, of philosophy, of culture. What music will we compose after seeing a sunset on a world with twin suns? What philosophies will emerge when we can walk on the surface of a dozen different Earths? And perhaps, just perhaps, we would finally answer the oldest and most fundamental question we have ever asked. Are we alone? The successful construction of a warp drive or a wormhole network is not just an engineering milestone. It is the catalyst for the next stage of human consciousness. It would be the moment we graduate from being a terrestrial species to being true citizens of the galaxy. It is the moment our search for meaning goes interstellar. This technology would not just change our capabilities. It would forever change our perspective of ourselves and our place in the universe. It would be the ultimate fulfillment of our exploratory drive, the final and most complete expression of what it means to be human. Our investigation is now complete. We have journeyed from the edge of impossibility to the blueprint of a new human destiny. Let us, for one final time, review the case file. We began with the cosmic crime scene, a universe so vast and governed by a speed limit so absolute that it sentenced humanity to solitary confinement on a single, fragile world. The laws of special relativity stood as the unshakable warden, presenting a perfectly constructed prison. Relativistic mass, infinite energy requirements, and the tyranny of the rocket equation were its bars, seemingly unbreakable. The initial verdict was clear: impossible. But we refused to close the case. We suspected that the laws of physics were not just a rule book of limitations, but a complex tapestry of possibilities. And so our detective work began. We dusted the cosmos for clues and found them not in some violation of the rules, but deep within the architecture of the rule book itself, in the elegant, mind-bending principles of general relativity. We discovered that space-time was not a rigid stage, but a pliable, engineerable material. We found proof in the bent light of distant galaxies, in the superluminal expansion of the universe itself, and in the topological tiers of black holes. These clues led us to a stunning breakthrough. We connected them to two concrete engineering blueprints, the wormhole and the warp drive, and in doing so, we uncovered the unifying secret, the single key that could unlock both: the theoretical, yet physically plausible, existence of exotic matter and its property of negative energy. The case had a solution. From there, we laid out the multi-generational construction plan, a project of almost unimaginable scale, moving from the quantum spark of the Casimir effect to the star-forging foundries of the future. And finally, we dared to envision the legacy of such an achievement: a future free from scarcity, free from the threat of extinction, and ignited by a renaissance of discovery that would redefine our species. If there is one singular, critical finding to be drawn from this entire investigation, it is this: the quest to break the universe's ultimate speed limit is not a problem of propulsion. It is a problem of geometry. For all of our history, our engineering of movement has been defined by a single paradigm: applying force to an object to push it through a medium. A stronger oar to push through water, a more powerful engine to push through air, a bigger rocket to push through the vacuum of space. We have been trying to build a faster ship. This investigation has proven that this path is a dead end. The universe has placed a fundamental limit on how fast any ship can travel. The true path, the ingenious connection that resolves the entire case, is to stop trying to build a faster ship and start trying to build a better ocean. The solution is not to outrun the law, but to reshape the landscape on which the law operates. We are not aiming to travel through space at impossible speeds. We are aiming to reconfigure the very distance between 2 points. We are seeking to fold the map, not just drive across it faster. This is a paradigm shift more profound than the transition from sail to steam or from propeller to jet. It is a transition from thinking of ourselves as passengers within a static universe to thinking of ourselves as architects of a dynamic one. This is the core engineering lesson, the central truth upon which our entire interstellar future rests. But this raises a final, deeper question. Why? Why pursue a goal so distant, so monumentally difficult, that its realization may lie centuries or even millennia in the future? The legacy of resource abundance and species survival are powerful motivators, but they do not capture the true, primal reason we look to the stars with such longing. The answer is simpler and far more profound. We reach for the cosmos because it is in our nature to reach. We are the descendants of explorers, of innovators, of individuals who stood at the edges of their known worlds and felt an insatiable pull to see what lay beyond the horizon. It is the same impulse that drove the first humans out of Africa, that sailed Polynesian navigators across the vast, empty Pacific, that pushed mountaineers to the frozen peaks of the highest mountains, and that strapped astronauts to rockets and flung them towards our own moon. This quest is the ultimate expression of that innate human spirit. It is curiosity forged into an engineering challenge of cosmic proportions. The complex physics and the grand construction plans are merely the modern language we use to describe our oldest, most enduring desire, to explore, to understand, and to transcend our limits. The engineering is the tool, but the human dream is the true protagonist. And so, while the construction of a warp drive or a stable wormhole remains a project for our distant descendants, our role in that great endeavor is happening right now. We are living in the foundational age, the critical phase zero of this plan. Every theoretical physicist who refines our understanding of quantum gravity, every materials scientist who designs a new metamaterial, every aerospace engineer who pushes the boundaries of energy and propulsion is, whether they know it or not, laying another stone on this long road to the stars. The theories they formulate, the materials they create, and the technologies they invent will be the classical knowledge upon which the quantum engineers of the future will build. Our guide to breaking the speed limit is not a fantasy. It is a declaration of intent, a statement of faith in the power of human ingenuity to solve the problems of tomorrow. It is a legacy we are building today, in our laboratories, in our supercomputers, and in our dreams. The universe does not give up its secrets easily, but it has left us clues. The path is not blocked. It is merely hidden, waiting for a species with the courage to see it and the persistence to walk it. The stars are not just distant lights in our sky. They are our inheritance, and that inheritance will be claimed, not through conflict or conquest, but through the quiet, relentless, and audacious power of engineering, applied on a cosmic scale. The investigation is closed, but the journey has just begun.